Section 5.7, Solving Linear Inequalities in One Variable. Definition: a linear inequality in one variable. A linear inequality in one variable is an inequality that can be put into one of the forms shown below. What I want you to see about these four forms is they basically look like y equals mx plus b, the equation of a line, and that's why we're talking about them as linear inequalities, except that instead of the y, they've put a 0, and then instead of an equals, it becomes an inequality because it has either a less than or equal to, a greater than or equal. And then m and b are constants, and m can't be 0. And that's the format that we're going to be working with. Another definition: solution, solution set, and solve for an inequality in one variable. We say that a number is a solution of an inequality in one variable if the number satisfies the inequality. And the solution set of an inequality is the set of all the solutions of the inequality, and we solve an inequality by finding its solution set. So let's put those definitions into action with an example. Sketch the graph of the inequality x is greater than or equal to 1. So first of all, it's worth pointing out that maybe doesn't look exactly like any of these formats. It has the greater than or equal, which matches this. But where's the 0? Where's the m? Where's the b? Well, I think you could argue the m is 1 in front of the x, and the b has just been moved over to the other side, and that's where the 1 is coming from. So these inequalities don't always look exactly like these forms, but they could be put in those forms. Now, to solve an inequality, or to sketch the graph of an inequality, really does mean to solve it, because a graph is just a picture of all the solutions of an equation or inequality. So to graph this, what I would do is start off with the number line. I would put the number over here on the graph, usually right in the center. And then I would think about, does that number solve the inequality or not? So is 1 greater than or equal to 1? Because of the or equal part on there, which is what this extra line signifies, I would say that 1 is a solution because 1 equals 1. So when that endpoint is a solution, we put a circle around it, and then we make that circle filled in or solid. And then what else solves this? Well, anything that is greater than 1 also solves it. And on the number line, if something's greater than 1, then it's on the right of 1. Just a quick comment about the graph. When we do these graphs by hand, generally we will raise the graph up a little bit to make it easy to see. I'm using two different colors here, black and purple, but even then they kind of look somewhat similar. And if I drew one right on top of the other, they would start to blend together and be hard to see. So in the textbook, on the computer, a lot of times you'll see these lines just drawn right on the number line, but it's easier for them to make colors that are distinguishable in those formats than when we do it by hand. So the standard for by hand is to raise that graph. Let's look at another example that points out some of the differences. When we move to x is greater than -3, I would have the same approach, which is to start off with the number line, put this number in the center, -3, and then think about, does that number work or not? So is 3 greater than -3? And the answer there is no. So I put an open circle around it, and this time I don't fill it in because -3 does not work. I still want the numbers that are greater than -3, and those would be to the right, so I draw an arrow to the right from there. A lot of times I'll get the question, could I have just started at -4, made it solid, or sorry, I guess that'd be -2 on this side, make it solid and move over with the graph? But the answer is no. I'll go ahead and put that -2 on the number line, -4 maybe over here. If I were to move the circle over to -2 and make the graph go from there, I'd be missing numbers like, say, -2.3, -2.8. Those would be in that section that would now be excluded. But those things actually do solve this because they are to the right of -3 on the number line. All right, and then looking at the idea of solutions, we can see from these graphs that inequalities have many solutions, not just one. And if you wanted to test an individual number to see if it was a solution, we do the same thing we would with an equation. We plug it in and we see if it works. So considering the inequality 3x plus 5 is greater than or equal to 14, do any of these numbers, 2, 3, or 6, satisfy that inequality? So the way we want to check that is by plugging them in. So for the first one, we write 3x, but instead of the x, we substitute the 2. And then we still have the plus 5 and the greater than or equal to 14. And we just want to ask this question, is that true or false? So we simplify it. 3 times 2 is 6. Plus 5 is greater than or equal to 14. We're wondering, is that true? but 6 plus 5 is 11, and 11 is not greater than or equal to 14. So this statement right here is false, so we can put that line through it. And because it didn't work, when they ask is that a solution, is 2 a solution, I would say no. And then we just do the same thing for the other two and see if they work or not. So we're going to write 3x, but this time instead of the x we're going to put the 3. And then plus 5 is greater than or equal to 14, just substituting that 3 in place of that x. And checking to see if it's true, we simplify. We get 3 times 3 is 9, plus 5 is greater than or equal to 14. Continuing to simplify, 9 plus 5 is 14. And because we have the extra or equal to line there, we can say that 14, because it's equal to 14, does satisfy 14 is greater than or equal to 14, so I'll say yes for that one. And then we want to move on and check the 6. So doing the same thing, we substitute the 6 in for x. 3 times 6 plus 5, is that greater than or equal to 14? So we simplify. 18 plus 5, is that greater than or equal to 14? And then finally we get 23 is greater than or equal to 14, and that is true, so I'll put a check mark, and we have another solution. So of the 3 numbers we tried, we see that 2 of them are solutions. Sometimes when I'm doing this and I get one solution, people will think, well, why are you even trying for another solution? You've already found the solution, so you should be done, right? Well, we see that's not the case because there are 2 solutions here. We can also see that from our graphs, because when we draw this graph to the right, we're saying any number bigger than -3 works as a solution to that inequality. So inequalities have many solutions, not just one, not even just 2. It's generally infinitely many. So now we want to start looking at what is the procedure for figuring out what are all the solutions, so we don't just have to test one by one, but we can come up with a solution set right away. So we'll see that as we continue on. Before we start learning the steps to solve inequalities, it's worth looking at the graphs in a little bit more detail, seeing how they're connected to solutions of inequalities, and then also to introduce something called interval notation and see how that's connected. So if the solution was x is less than 3 in symbols, what would it look like on the graph? It would be an open circle around that 3, and then because x is less than 3, it would be to the left of 3. So this is pretty hard to see on this picture, but they've actually drawn an arrow to the left. And if we were looking at it in the book, we'd see one color on top of another, and it might stand out. Here, it just looks like black on black, and it's hard to see. So this is why I think it's a good idea to draw your graph elevated instead of right on the number line, and I'll just retrace this to show that that was an open circle. It's an open circle because this did not have the or equal. So we see here when the or equal does show up, it's a solid circle, and they again went to the left, but it's again hard to see, so I think it would be better to show that as an elevated graph. If you have a greater or a greater than or equal, then those graphs are going to go to the right rather than the left. And again, we see that connection where if there's no or equal, you have an open circle, but if it is there, you fill it in. I'll fill those in too with this pen just so it looks a little bit more consistent. But or equal to line, solid circle, no or equal, open circle, left versus right is based on is it a less or is it a greater. Now interval notation is a way to write that infinite set of answers in a short format that's not graphical. And to do that, you write the number that is your left boundary and the number that is your right boundary, and then either parentheses or a square bracket. We put square brackets when numbers are included on the boundary. We put open parentheses, the rounded, when that boundary is not included. Negative infinity and positive infinity are more concepts than numbers, so you can go towards negative infinity or positive infinity, but you can never reach those destinations. So in that sense, they could never be included, so we put them open. So this graph goes forever to the left, so its left-hand boundary is negative infinity. It stops at 3 on the right, so 3 is its right-hand boundary. The 3 is not included, so open parenthesis. This is the same graph, but the 3 is included, so we indicate that with the squared off bracket instead of the open parentheses. Here, these on the left have a boundary of 3. On the right, they go forever. So left boundary 3, right boundary infinity. The 3 not included here, so rounded. The 3 is included here, so squared off. And infinity never included, so parentheses. And we'll get some more practice with that in the examples below. Alright, so let's go ahead and look at some examples. This will give us practice with graphing and interval notation, and also just with solving inequalities in general. So solve each of the inequalities, describe the solution using an inequality, interval notation, and a graph. So the main thing to know here is that solving an inequality is almost identical to solving an equation. So we're going to think about the same steps and connections as we do it. Our goal is to get x by itself. So we look at what's with the x, plus 5. How is it connected? Addition. So how would we get rid of it? Subtraction. And just like in an equation, if you subtract 5 from one side to cancel off the 5, you have to subtract 5 from the other side to keep it balanced. Simplifying, on the left side we only have the x, the symbol stays the same, and 9 minus 5 becomes a 4. So x is less than or equal to 4 is our solution set. So that would be describing the solution with an inequality. They want us to do an interval notation next, but I find it's easier if you do the graph and then from the graph get the interval notation. So let me do the graph. So I'm going to draw a number line. I'm going to put the number that ended up isolated there, the 4, in the middle. And then I'm going to think about, is that a solution, yes or no? Well, because of the inclusion line, 4 is a solution, so I'll put a solid circle. And go ahead and switch to the color there. So a solid circle at 4. And it says x is less than or equal to 4, so the solution should be to the left side. And then as far as interval notation goes, what are the answers that work? On the left, our graph goes forever, so we have negative infinity. On the right, we have the 4, so those are our two boundaries. Negative infinity can never be included. The 4 has a solid circle because of the or equal to, so it is included, and we put the bracket to indicate that. And then just to see if that worked, we can test a couple numbers. So this is optional, but let's think about the numbers that have this surrounded. On the left, you have numbers like 3. On the right, you have a number like 5. So when I say that this part right here is the solutions, I'm saying 3 because it's covered by the graph works, but 5 because it's not covered does not work. So let's just check that real quick. Is 3 plus 5 less than or equal to 9? That's 8 is less than or equal to 9. That's a true statement, so yes, that's a solution. And that's good because 3 is covered by our graph, so we're saying it was a solution. How about the 5? 5 plus 5, is that less than or equal to 9? That would be 10 is less than or equal to 9, which is not true. So that is not a solution because that's false. So I would say no, that one doesn't work. And does that match the graph? Yes, because 5's over here, which is not covered by the graph. So it does look like this process is working. Let's continue it now using part B. So a different step has to get used here. We're trying to get x by itself, so we're trying to get rid of that 2. How is it connected to the x? By multiplication. So how would I get rid of it? Through division, because the 2's will cancel. 2 over 2 is 1. 1 times x is just x. Simplifying on the other side, negative 10 divided by 2 is negative 5. And then moving on to the graph and the inequality, let's take a look at that. For the graph part, we put the negative 5 in the middle. And then is negative 5 included? No. So we do an open circle. What side are the solutions on? X is less than negative 5 are solutions. So we go to the left. So, just like in solving equations, if you're trying to get rid of a plus 5, subtract 5 from both sides. Trying to get rid of a times 2, then divide by 2 on both sides. So let's look at the one step where solving an inequality is different from solving an equation. And that comes with dividing by a negative. So if you have this multiplication connection right here, you'd want to get rid of that negative 2 by dividing by negative 2. But there's a special rule in this case, which is if you're solving a linear inequality or any inequality and you divide by a negative, then when you do that, you have to take the inequality and reverse its direction. So that less than or equal to becomes a greater than or equal to. And I'll show you that that was indeed necessary as we move forward, but let's go ahead and finish it off first. The negative 2's cancel, and I have w by itself. My inequality has been reversed, so it's a greater than or equal to now. And 14 divided by negative 2 is negative 7. For the graph, we're going to go ahead and put the negative 7 in the middle. And we're going to think about, is it included or not included? Because of the or equals, it's included, so I'll put a solid circle. And then it's a greater than, so we would go to the right. So that's the claim that that's the answer. But there was that weird part where I reversed the inequality, right? So was that really the right thing to do? Let's put numbers on both sides. To the right you might have a number like -8, and to the left and to the right you might have something like -6. If it was correct for us to reverse that inequality, -6 will work and -8 will not. So let's check the -8 and see if it works. -2 times -8, I'm claiming that is not going to work. So originally we had a less than or equal to 14. So if that's a solution, it should work. I didn't shade it, so I'm saying it's not a solution. And that's good because the statement is 16 is less than or equal to 14. That is false, so that's not a solution, and that's good because it was not included in my graph. How about the -6? -2 times -6, is that less than or equal to 14? Multiply those together, you get 12. That is less than or equal to 14, so that one's a yes, which is good because the -6 was shaded. Alright, so both of those we solved and did the graphs, but I didn't do the interval notation on them yet, so let's go back up and finish that part off. Let's go ahead and go up and do this one. It goes forever to the left, so -infinity is the boundary on the left side. On the right side, -5 is the boundary. -infinity can never be included because this is an open circle, that's not included either. Taking this one and changing it to interval notation, the left-hand boundary is -7. Goes forever to the right, so the right-hand boundary is infinity. Infinities are never included. And this -7 has a solid circle, so it is included. So there's our solve, graph, and interval notation. Solve, graph, and interval notation. And we see this new rule coming up that if you divide by a negative at any point, you would have to reverse the direction of the inequality. Turns out that's also true if you multiply by a negative, but that's a more rare step. But the complete rule would say if you multiply or divide by a negative when you're solving an inequality, you reverse the direction of that inequality. So we'll start off with the solving process, which is very similar to solving a linear equation. So our goal is to try and get this x by itself, and we're going to take steps to try and make that happen. The first thing I'd want to do here is move this +7 to the other side. I would do that by subtracting 7 on both sides. That would cause that to cancel over here, and I would have 4x is less than 8. And then I'm trying to get that x by itself now, and it's connected to the 4 by multiplication. So I would divide both sides by 4, which would cause that 4 to cancel. And we saw that sometimes you have to switch this inequality, but that's only if you divide by a negative. We're dividing by +4 here, so we don't have to make a switch on that. So it'll just be an x on the left, it'll still be a less than, and 8 divided by 4 is 2. So there's one part of our answer. There's the solution expressed as an inequality. Then they want us to write it using interval notation and also to do a graph. I actually find it a little easier to do the graph first and then write the interval notation from that, and the order doesn't really matter. I would just take whatever number came up here and put that in the middle of my graph. Because it says x is strictly less than 2, I would do an open circle to show that the 2 is not included. And when your x is on the left side, the arrow points the way you want to go. Our x's are to the left of or smaller than 2. So that would be like this. And then the interval notation would be that this goes forever to the left, which is -infinity. And on the right hand side, it stops at 2. But 2 is not included, so I would use rounded parentheses to illustrate that. Alright, so there's our solution as an inequality, there's the graph, and interval notation. Let's try another one. 5k minus 1 is less than or equal to 2k plus 8. I would want to get the values of the variable on one side, the numbers on the other, so I'll move the values of k to the left. So my first step would be to subtract 2k from both sides. Those cancel. I get 3k minus 1 is less than or equal to 8. I would add 1 to both sides to move the numbers to the right since I kept the variable on the left. And I get 3k is less than or equal to 9. 3 is connected by multiplication. Get rid of it by division. And it looks like k would be less than or equal to 3. And then the graph of that, I would do my number line. I would put 3 in the middle. You could start with an open circle if you want, but because this says or equal to, we're going to close that circle in. That's the way we show that the 3 is included as part of our solution. The arrow, when k is on the left, will point in the direction we should draw our graph. the values of k we want are the ones that are smaller than or to the left of 3. So I start at that 3 which is included, draw an arrow to the left illustrating my solutions. So there's the solve, there's the graph. The interval notation always goes from left to right. On the left hand side our boundary is negative infinity. We always put rounded on infinities because we can't ever reach them, so they're always listed as not included. On our right, the graph ends at 3, and the 3 is included, and we illustrate that by using the squared off bracket instead of using the parentheses that are rounded. So solution, graph, and solution in interval notation. Alright, let's go ahead and look at one more on this page. This one just has a little bit more simplification to do. When we have parentheses, I would start off by using the distributive property to clear those. So distribute the 4, 12x, and 4 times negative 5 would be minus 20. That's greater than distribute the 5. 5 times 2x is 10x, and 5 times negative 3 is negative 15. And then I'd want to move the x's to the left and the constant terms to the right. So subtract 10x from both sides to get rid of this one on the left and move it, on the right, move it over to the left. I like to sometimes at the same time move my constant term over, so if I add 20 here, that would cause that to cancel. 20 on the other side keeps things balanced. Over here, 12x minus 10x would be bigger number's positive. So positive 2x is greater than negative 15 plus 20 would be 5. And then divide both sides by 2 to get rid of this 2. And it looks like the solution would be that x is greater than 5 halves. And normally when I go to graph something like 5 halves, I might think of it as a mixed number and say 2 goes into 5 twice with 1 left over, so this is 2.5. And that would tell me, okay, I need to plot that halfway between 2 and 3. But really when you're doing inequalities, we typically just put one number on there, which is this number. We indicate whether it's included or not. This one's not included, so I would do an open circle. The arrow points the way. If x is greater than 5 halves, then x is to the right of 5 halves, so my graph would go like this. When I go to do the interval notation for that, the left-hand boundary is 5 halves, which is not included because of the open circle and then no equal portion line there. And then on the right, we go forever or to infinity, which can never be included, so that would be rounded. So solve, graph, interval notation. Those are the 3 ways that we would express those. Alright, let me show you one more example of solving an inequality. And again, our directions would be to solve, graph, and write the answer in interval notation. And when I look at this one, the first thing I notice is that it has fractions. And just like we can solve an equation with fractions by multiplying through by the LCD, we can do the same thing if it's an inequality. So the least common denominator of 3, 6, and 2 would be 6. That's divisible. All 3 of these go into 6 evenly. So I would take each term and I would multiply that by 6. So 6 times 5/3 minus 6 times 1/6 x, and that would still be less than 6 times a half. It would still be less than because as long as we're not multiplying by a negative, the inequality continues to point in the same direction. And then just showing the canceling here, and this is the reason we multiplied by the 6, is it should make all the fractions go away. This denominator of 3 goes into this 6 twice. This denominator of 6 cancels that 6. This denominator of 2 goes into that 6 3 times. So if we look at what's left over, in the first term we have 2 times 5, so that's 10. Here the 6's are gone, so we just have minus 1x, or just minus x. And on the other side we have less than 3 from the 3 times 1. And then we could subtract 10 from both sides. Those cancel. At that point it looks like I'm done almost. Negative x is less than, let's see, 3 minus 10 would be negative 7. But we don't want x by itself, or negative x by itself. We want x by itself. So I still have to get rid of that negative, and I would do that by dividing by negative 1. But if I divide by negative, I have to flip the direction on that inequality, or reverse the direction on that inequality. So that's going to become a greater than at the moment I divide by negative 1. And so the 2 negatives here cancel, and I get positive x is greater than negative 7 over negative 1, which would be positive 7. And then for the graph portion there, I would put the 7. There's no or equals, so an open circle. X is greater than or to the right of 7. And that would be my graph. Interval notation, left-hand side of the boundary is 7, which is not included. And it goes forever to the right, or to infinity, which is never included. So there's my solution, my graph, and the interval notation. And again, the key step here that makes this an easier problem is to notice the fractions at the beginning, figure out their least common denominator, and multiply every single term by that. That should eliminate all your fractions and make the rest of the work go smoother. So as we go through and we solved all these examples of inequalities, we should notice it's just like solving an equation. There's really just one difference in the solving process, which we saw right here. If at any point along the way you divide by a negative, then you're going to reverse the direction of the inequality. That would also be true for multiplying by a negative, but that's actually very rare. So it usually is a division step, and it's usually the last step. So you're trying to get x by itself, you divide by its coefficient. Sometimes that coefficient is negative. If that's the case, you have to reverse the direction. So that's the key thing to remember about solving linear inequalities, is if we multiply or divide both sides of an inequality by a negative, then we must reverse the direction of that inequality. And except for that step, it doesn't feel much different to solve an inequality versus an equation. There are the extra steps, though, of doing the graph and the interval notation that tend to go with these. So a lot of times we have 3 parts to our answer. But as far as the algebra goes, this is the only step that feels different. Alright, let me go ahead and show you another type of inequality called a compound inequality, or sometimes I'll refer to it as a 3-part inequality, where instead of just a left and a right-hand side, we have a left side, a right side, and also a middle. And when we're trying to solve this type of inequality, our goal is generally to try and get that x by itself in the middle. And so you kind of focus just on that middle piece, 3x plus 1, and you think, if I wanted that x by itself, I'd have to get rid of that 3 and I'd have to get rid of that 1. Following the normal order that we do with equations, I would try and get rid of that plus 1 first, and I would do a minus 1 to get rid of a plus 1, and those would cancel. When we're doing an equation or a standard inequality, we say if you're going to subtract 1 from one side, you have to subtract it from the other as well. When you're doing a 3-part inequality, if you subtract 1 from one part, you have to subtract 1 from all 3 parts to keep that balanced. So we do negative 5 minus 1 is negative 6. There the 1's canceled, so we have less than or equal to 3x, and less than or equal to right here from there, and then 13 minus 1 would be 12. We're closer to our goal, but we're not there yet. We want x to be by itself in the middle, and we still have that 3 in front of the x. It's connected by multiplication, so I'd get rid of it by division. And again, with 3-part inequalities or compound inequalities, if you're going to divide one part, you divide all parts. So I'm dividing the middle by 3 because that cancels that and leaves the x alone. I'm dividing the outsides by 3 to make sure I keep balance. And then just looking at where that would take me, on the left I have negative 2. That's less than or equal to x, which is less than or equal to 12 over 3, which would be 4. And then that's the solution. Once you get that x by itself, we'd say you've solved it. The graph part, I would put both of those numbers, the negative 2 and the 4. I would think about whether they're included or not. They both have the or equals, so they both get solid circles. And then where's the x? The x is in between negative 2 and 4, and so our solution graph is that portion of the number line that is between negative 2 and 4, and including negative 2 and 4 because the extra lines. And then for interval notation, where's our graph start on the left? Negative 2, which is included, so square bracket. And on the right, it ends at 4, which is also included, so another square bracket. So that's how you would solve a 3-part inequality. Your goal is to get the x by itself in the middle. You think about it the same way. If you want to get rid of a plus 1, subtract 1, but do it from all 3 parts. You want to get rid of that 3 times in front of the x, divide by 3, but do that on all 3 parts. And then typically when you go to graph one of these, since the x is in between those values, your graph will be drawn in between those values. Let's take a look at one more, just to get some extra practice with that. So again, it's a 3-part inequality. We have 7 on the left, 5 minus 2x in the middle, and 13 on the right. Our goal is to get that x by itself. I have to get rid of the 5 and the negative 2. We usually try and get rid of the terms, the constant terms first. So I'd subtract 5 to cancel those, but I have to do that on the right and the left as well. On the left, 7 minus 5 is 2. We had our 5's cancel in the middle. The less than copies down, and I have negative 2x. The less than or equal to copies down, and 13 minus 5 would be 8. So I'm almost there. I just want to get this x by itself. There's a negative 2 that's multiplying that, so the opposite of that would be to divide by negative 2. If I do that in the middle, I have to do it to all three parts. I'm doing it in the middle to make those cancel. But we still have to remember that when you're working with an inequality, whether it's the simpler type or this compound three-part type, if you divide by a negative, you have to reverse the direction of your inequality. So this less than switches to be a greater than. That less than or equal switches to be a greater than or equal. And so when I look at where that puts me, 2 over negative 2 is negative 1. This is now a greater than. The x is now by itself. This is now a greater than or equal, and 8 over negative 2 is negative 4. One thing that should always be true with the three-part inequality is that two inequalities, if you think of them as arrows, should point in the same direction, and they should point to the smaller number. And negative 4 is smaller than negative 1, because if you think of that on the number line, negative 4 would be to the left of negative 1. And when I go to graph this, I would actually like to see the numbers in the same order here as they are there. So when I divide by negative and get these pointed to the right, I usually want to go ahead and flip everything around and put the negative 4 and the x and the negative 1 and just take these symbols with it. That was in between the x and the negative 4, and it was pointing at the negative 4, so it still points at the negative 4. That symbol was between the negative 1 and the x, and it was pointed at the x, so it would still point at the x. So you could do your graph from here, but personally I always like this to go from small to large because that's the way my graph is going to look, and that's the way my interval notation is going to be written out. So I find it smoother if I do it that way. And then I can say the negative 4 is included, solid circle, and the negative 1 is not included, so open circle, and x is in between those two, so the graph goes in between those two. And for interval notation, the left boundary is negative 4, which is included. The right boundary is negative 1, which is not included. And that would be my solve, graph, and interval notation. I would argue this is a correct solution too, but I just prefer it to be smallest number on the left, bigger number on the right, so I just kind of reverse that whole thing at the very end. Okay, let's finish up by looking at an application of inequalities. The number of married coupled households in millions and the percentage of households that are married couple households are shown in the table for various years. So we've got 93, 95, 2000, 2003, and 2007. We have the number of married couple households in millions, and we can see that the number of married couples is increasing. And then we have the percentage of households that are married couples, and we can see that those are decreasing. And let's see what they want from us. Let f of t be the percentage of households that are married coupled households at t years since 1990. Find an equation for that function f of t. So they've given us 3 columns here, so we do have to sort out what's kind of our input, what's our output. Looks like the input is t, but remember the year isn't t. T is the number of years since 19, where'd they go with 1990? So in 1993 it had been 3 years, in 95 it had been 5 years, in 2000 it had been 10 years, 2003 13 years, in 2007 that would be 17 years. So always adjust those years over to t by thinking about what the starting point was. So there's our input, and it says that f of t, which is the output, is the percentage. So these are our values of f of t or of y over here. So this one is just kind of extra. We'll see why they put that later, but for now, when they give us 3 columns, we have to sort out what's the input-output. So t is the input, so we figured that out. It says that f of t is the percentage, so we pick that column to be our output. Now they want us to find an equation, and so if that is going to be a linear equation, then what we'd want to use is regression to model that. So what I'm going to do is put that data into the calculator. So let's bring the calculator in. I'm going to want to go to Stat and then choose Edit. And my columns are cleared out, so in L1 I'll put the t's, 3, 5, 10, 13, and 17. And in L2 I'll put my outputs, so 55.1, 54.4, 52.8, 51.5, and 50.8. And then I'm going to use linear regression to try and come up with a function. So I'm going to think of that function f of t as being of the y equals mx plus b format. So that would be f of t equals m times t plus b. And now I want to use the calculator to figure out what is the slope and what is the intercept for this situation. I think before we do that, it would probably be good to have a quick look at the graph of this data to make sure linear is really appropriate. So I'm going to take the window, and then for the minimum I'm going to go with 0 and 20 because those are a little smaller and a little bigger than the minimum and maximum for t. We could count in 1s or 2s, it doesn't matter too much. I guess I'll just leave that as a 1. And then on our outputs, they go from 50.8 to 55.1, so I'll go from a low of 50 to a high of 56, just giving myself a little room up below the smallest and above the biggest. And then 50 to 56 isn't a very big span. I don't want to count in 5s, which is there now. I'll change that to a 1. I'll check my y equals to make sure the plot is on and there's no other equations there. So now let's take a look at the graph. And that's not perfectly linear, but it does look like it's roughly linear. So finding an equation of this format does seem to make sense to me. So I'm going to hit Stat, Calc, Linear Regression. Data is in L1, L2. Press Enter, and the calculator will tell me the values of the slope, which they list as an A, and of the b, which they list as b also. So we will write f of t is approximately, and I don't think they gave us any rounding rules here, so we'll just go ahead and put several decimal places on each one. So for the slope, negative 0.3183, and then that's times t, plus the b, which is 55.9756. So there's our equation, and we can check real quick just to make sure that that's a good fit. If I hit y equals on the calculator, I can enter that in, negative 0.3183 times t. I have to use an x on the calculator, plus 55.9756. And when I hit graph, I see that equation drawn in with the data, and I see that it is in fact a pretty good fit. All right, let's go ahead and make use of that equation now and see where the inequality piece enters into this. In which years were more than 53.4% of households married couple households? So in which years? So they want us to find values of t, it sounds like. Were more than 53.4% of married couple households. All right, so let's see. F of t is the percentage of married household couples, and they say they want that percentage to be more than, so greater than symbol, 53.4. So this is the percentage of married couples. That's what our function stands for. They want that to be more than 53.4%. But they want us to figure out in which years, so they want us to solve for t. So the way I'm going to get t into this is substitute this side of our equation in place of the f of t. So I'm going to have negative 0.3183t plus 55.9756. That's f of t, so that takes the place of the left side. And we want that to be greater than 53.4. So I started off with the f of t because they were talking about the percentage of married couple households, but then I'm substituting in what f of t equals so that I can get at the year. From there, it's the kind of steps we've been learning in this section, trying to get t by itself. There's a plus 55 here, so let's subtract that 55.9756 from both sides. No need to reverse the inequality. Subtraction doesn't cause that to happen, only multiplication or division by a negative. So I'll cancel those off, and that puts us at negative 0.3183t, and then I'm going to go to the calculator to think about that subtraction just to make that go faster. So I'll get that graph out of the way, and we have 53.4 minus 55.9756. So I get negative 2.5756, and I'm still trying to work on getting that t by itself. So the negative 0.3183 is connected to t by multiplication. So I would divide both sides by negative 0.3183. I'll cancel that off. Divide on the other side to keep things balanced. And then, because I'm dividing by a negative, I have one extra thing I have to do, which is take this greater than and change it to a less than. Because when you divide by a negative like we are there, the inequality will reverse. And then finishing that off, that's now a less than, so t is less than. And we're going to bring this in and do the division. We have the negative 2.5756. We're going to divide that by negative 0.3183, and we get t is less than 8.09. So if we thought about that graphically, which they're not asking us to do, we have the 8.09. 8 would be to the left, 9 would be over here to the right. This number is not included, but we want everything that's before, so that would be 8, 7, 6, 5, and so on, but not 9, 10, 11, and so on. So 8 is the first one that would be included, and t is less than 8.09 for a whole year. And since they started the clock on us in 1990, if I add the 8, I get 1998. And they asked in which years, so I would say 1998 and before that. So in which years were more than 53.4% of married couple households married couple households? 1998 and before that would be the answer. Let's just think about real quick, does that make sense? So we look at the percentage, and we notice that the percentages are getting bigger. So if they want it to be more than 53.4, then that would be somewhere in between these is where 53.4 happens, and going that way is when it would be more. We came up with 1998, which is in between the 95 and 2000, and we said before, which makes sense because the 95 and 93 are the ones that work and are bigger than that. So the inequality helped us figure out what year that happened, even though that year didn't show up in our data set. All right, let's finish this off with one follow-up question. Although the number of married couple households is increasing, the percentage of households that are married couple households is decreasing. Explain how this is possible. So this is a little bit of a tricky question to answer, but when you think about the percentage of married couple households, percentages come from a fraction. You'd take the number of married coupled households, and then you divide it by the total number of households. And what they're saying is it seems strange that if the number of married couples is increasing, that the percentage could be going down. And that's true if the total number of households stayed the same. But if the numerator and denominator are both changing, then it's possible that the numerator can get bigger and the overall fraction can get smaller. So, for example, suppose you had a fraction like 8 over 16. So that would reduce to 1/2. Is it possible, right? So that's equal to 0.5 or 1/2. Is it possible that the numerator could get bigger and the percentage, right? What's the percentage there? 50%. Is it possible the numerator could get bigger and the percentage would still get smaller? Sure. Suppose the numerator went up to 9, but that the denominator went up to 20. So that would be an increasing numerator. But what happens to the percentage? Well, if you do 9 over 20, you get 0.45, which is 45%. So there's an example of the numerator growing and yet the percentage going down. So in our example, the number of married households is increasing, but the percentage is going down. Why is that? Well, because the total number of households is growing at a rate where even though the numerator is getting bigger, the overall fraction is getting smaller. So it is possible to see the number of married households going up and yet the percentage going down, even though that might at first seem a little counterintuitive. All right, that wraps up section 5.7.